Yeah. Okay. So we need to look at the relationship when all variables are considered at the same time. So baru point ni baru you boleh tengok balik I punya suara lah. I boleh dengar balik I punya suara. Kalau tak, you tengok I punya slide saja. Right. Okay. This is a simple linear regression for H and PFR. What can you conclude from the result? What can you conclude from the result? Based on the scatter diagram, apa yang you boleh conclude? There is a weak linear correlation between H and PFR, right? Because the scatter diagram shows that the data observation is dispersed from the predicted line. It's not really consistent through the line, right? Even though the scatter diagram shows a weak relationship, weak negative relationship, but if you look at the regression coefficient table, the p-value is less than 0.05, means that there is a significant relationship between H and PFR. However, if you look at the R square, 0.0479, it means that only 4.7% of the total variation in PFR can be explained by H. A very small contribution to the prediction outcome dependent variable, right? And if you look at the estimated standard error of estimate, it's quite large, 117. Just now we look at simple linear regression, only 0.17, right? This is 117, which is not, the model is not really good for prediction lah. But if you look at the p-value for F, still indicate less than 0.05. So means that in this stage, we need to consider other factor into the model as well. Right? So that's why we need to do multiple linear regression. So step in multiple linear regression. So now, first step in multiple linear regression or any analysis that you want to do, any statistical model or model machine learning classifier that you want to apply, you need to explore the data first. Understand the data. What is the mean of the data? What is the standard deviation? What is the minimum value, maximum value? Is there any outliers in the data? You need to identify first before we proceed with the analysis. In fact, the analysis will take only 2 to 3 minutes only, right? For data exploration will take longer time, right? So we need to clean the data, make sure data is well and ready for analysis. And the second step, we need to perform a univariable analysis, which is simple linear regression. Let's say we have 20 independent variables. We need to perform simple linear regression 20 times. Right? Simple linear regression 20 times, and we need to filter out the p-value, the simple linear regression that have p-value, right, less than 0.25 to be included into a variable selection process, into a multiple linear regression. Right. Some independent simple linear regression at univariable level is not significant, but when we input that variable into a multiple linear regression, it shows an important contribution, right? So that's why we take value less than 0.25 to be select as a in variable selection. Third stage is a variable selection. This stage we call as a preliminary main effect model. And then we need to check a multi-collinearity and interaction. Multi-collinearity means that there is a correlation between independent variable. If we have a high correlation between independent variable, then that should be a multi-collinearity issue. Later on, I will explain what is a multi-collinearity issue. And we check for interaction. This is what we call as preliminary final model. And next, we need to check the assumption line. In this case, we have another assumption line I. line, we know that linearity, independence, and normality, equality of variance. I means the independence of numerical variable, right? When we're done with the checking assumption, then we will get a final model, and then we can interpret and present the result. This is a step need to be taken for multiple linear regression analysis. Okay, so this is the assumption of multiple linear regression. Should be linear relationship, the residual should be small, same, this is the equal variance, and residual should be normal distributed, independent variable should not be correlated, multi-correlated issues should be avoided, and residual should be independent, right? So this is how we this is line I, linearity, independence, normality, homogeneity of variance, and fit of independent numerical variables. So how to measure this one? For linearity, we'll measure using XPYR. Homogeneity of variance, also same, XPYR. Independence of the sample should be settled during a study design. It means that the sample should be independent, not related to each other. Means that we should not have a repeated sample. That means we measure only one people one time. And normality of a response variable, we can draw histogram or box and whisker plot or any statistical measures such as Kolmogorov, Simonov, Sapiro-Wicks, Anderson-Darling, and so on. Right, based on our residual value, right? And then we fit the independent or numerical variable using XIYR. XI means the x-axis is an independent numerical variable, y-axis is residual value, right? Okay. So if you don't understand this one later on, you can rewatch my video ni dalam YouTube lah, right? Make sure you subscribe and click on the bell button. Right, this is the assumption that you need to check for linearity and equality of variance, right? Kejap kita sampai sini multi-correlativity and then kita take a 5-minute breaks. Okay, so this is how we check linearity and equality variance. If you still remember this one, linearity we check using XPYR. X-axis is predicted value, Y-axis residual. Sama juga with the equality of variance. So if the graph shows no pattern like this, right? Or means that the observation are scattered around the graph, right? So means that the linearity assumption is met and the equality of variance also met. If the graph shows some pattern, right? This is curve pattern, right? Non-linear pattern, right? So means that there are no linearity assumption and equality of variance is violated. Okay. So this is another form. It shows a no pattern. Okay. So this is an example by using Excel. I think I already showed to you just now. Right. So there are no sign of heterogeneity. This is very hard to spell to pronounce. Homogeneity of variance. This is an example of linearity, homogeneity of variance, normality, independence, and multicollinearity I will explain later. Right? And then we need to check the outlier before we proceed with the model fitness. Okay. This one done, right? Then we need. I'm going to explain about multicollinearity. So for multicollinearity, multicollinearity means that there are significant relationship between the independent variables. Right? Significant relationship between independent variables. So remember, in linear regression, we want to find relationship between independent variable and dependent variable. But instead of having relationship with dependent variable, the dependent variable also have relationship with another independent variables. Right? So this is what we call as multi-collinearity, right? So normally when the R value, the coefficient of Pearson coefficient of correlation shows 0.9 and above between the independent variable. So this might shows a potential of multi-collinearity. Okay. So the effect of multicollinearity, the important variable might end up to be unimportant, and the sign of coefficient might be in wrong direction lah. Maybe they should be in positive sign, but it turned out to be negative, right? And difficult to interpret, right? So to overcome multicollinearity, try to include many exploratory variables, right? That are independent to each other, or we can remove that variable that cause multicollinearity. But by doing this, maybe we will lose the important factor lah. Or we can try penalized methods such as lasso linear regression, rich linear regression, elastic net, penalized method lah. Okay. So this is example. If the correlation between 0.7, negative 0.7 to 0.7, maybe there are no multicollinearity. This is based on independent variable and independent variable, not dependent variable, independent variable, in between IVs, right? So in practice, if the correlation between the IVs, independent variables, more than 0.9, then we can say that it should be potential multicollinearity issues, right? So to calculate multicollinearity, to determine multicollinearity, we can use variance inflection factor, VIF. Variance inflection factor, VIF, is calculated by using R square. So this R square is not calculated by fitting dependent variable and other independent variables, right? Contoh, we have our dependent variable is pull strength, right? Our IVs, we have wire length and die height, right? So if you model dependent variable towards the independent variable, you will get R square. But what we need is we want to measure the relationship between the IV, right? We need to model another model, which is a wire length and die height. So model the independent variable among the independent variable. So one of the independent variable will become dependent variable, and this one stay independent, and we will get the R square. So this R square, we can get the value of VIF. So later I will show you how to get the value, right? So this is how we get the value. Let's say independent variable and independent variable, we got R square 0.24, and we put into the formula 1 divided by 1 minus R square. So we get 1.32. So as a benchmark, if the VIF more than 10, right, we will say that multicollinearity issue exists. If the VIF less than 10, there is no multicollinearity issue. Okay. Okay. Boleh? Oh, you nak rehat 5 minit. Okay. Alright, boleh continue. Dah habis sikit lagi. Boleh habis awal, kita boleh awal lah. Which is saya tak nampak pun boleh awal. Right. So this is a VIF, right, from statistical software, right? So VIF is calculated by using 1 divided by 1 minus R square for the model of independent variables. So if the value of VIF is more than 10, means that we can conclude that is a multi-collinearity issue in the model. And for next assumption that we need to check is normality of the error term, which is normality of the residual. We need to plot the normality by using a scatter diagram, or you can use a box plot, histogram to see whether the data is normally distributed or not. And for significance of regression, it's the same as previous. We already look at the ANOVA table, right? This is the first row is for regression. This is residual total. We have degree of freedom number 1, degree of freedom number 2, and this is a mean square regression, mean square error. And the square root of mean square error will be the standard error of estimate. This is the thing that we want to look at on the when we model the data. And the F value is taken from the mean square regression divided by mean square error. This is same as previous. Okay. So SSE, the standard error of estimate, should be the smaller. The smaller value of SSE should be indicate the successful of multiple linear regression. The R square is coefficient of determination. So if the R square approaching to 1 means that we have a strong relationship between the independent variable to dependent variable. T-test is we want to look at the relationship of independent variable and dependent variable. The F-test means we want to see whether the model is valid for prediction or not valid for prediction. Sama aja, it's the same as previous. The p-value, the smaller p-value less than 0.05 means we accept null hypothesis. Sorry, when the p-value less than 0.05, we reject null hypothesis. That means that the model is valid for prediction and there is a significant relationship. Now, let's look at data example number 2. We have pull strength, wire length, and die height. So I have 25 data. Let me show you by using Excel. So I think I already provide Python code in my website. You can look at, go to my website. Where is it? Right. In my website, I also provide Python code for example number 2. Right. You can look at here. But in this session, I'm going to show you by using Excel. So our pull strength is our dependent variable, where a wire length and die height is our independent variable. Assuming that we already checked the simple linear regression for each independent variable and found that each independent variable is significant, right? Assume that. So we want to proceed with multiple linear regression. So first we need to go to data analysis, and we need to find regression and click OK. So Y range should be pull strength. So you select everything, right, from pull strength until observation number 25. Right, for X axis, for independent variable, we set both wire length and die height. Okay, I select both. Saya dua-dua sekali. And then I check label, confidence interval, residual, not standardized residual. Standardized residual means I ignore the intercept, right? Because our model consists of intercept, y beta naught, right? So we need to look at unstandardized residual. Normal, probability plot, and residual plot. The output I'm going to put at G2. Right. Are you with me? Dah, ikut sekali. I click OK, and then you will get the result. So this is the table. I'm going to put here. Right. So first step, what we need to do, we look at summary table, right? Summary of regression statistic. So from here, we know that our R square is equal to 0.98, which is 98.11% of the total variation in pool length, pool strength can be explained by wire length and die height, right? The balance is 1.99, I think, right? Explained by other factors that not included in the model. Next step, we look at the standard error. We have a small standard error, 2.28, which is good, right? And then we look at the ANOVA table, right? This is the standard error, right? Square root of 5.523 is equal to standard error of estimate 5.235158, right? Is equal to standard error of estimate. Okay. Now, first step, we need to look at whether the model is valid for prediction or not valid for prediction. So null hypothesis, model is not valid for prediction. Alternative hypothesis, model valid is valid for prediction. Right, let's say our alpha equal to 0.05, test statistic, our p-value. So p-value is very small, right? 19 means 18 0 in front. So in this case, we're going to put like this, p-value less than 0.0001. It's not equal to 0, but it's very small, approaching 0. But it's not 0. Right? Our decision rule, if p-value less than alpha 0.05, null hypothesis is rejected. So our decision, since p-value less than 0.05, which is very small than alpha, null hypothesis is rejected. So we can conclude, conclusion, is the model is valid for prediction. Right. That is the first thing that we need. We're going to look at. The next thing, that's done. Done. The next thing that we're going to look at is our coefficient table. From the ANOVA, we know that the model is valid for prediction, right? So now, based on the coefficient table, right? So we know that our equation is y equal to 2.264. Maybe we take 2 decimal point lah. Later on, you can take 4 decimal point or 3 decimal point. Make sure standardize on your report. 2.26 plus 2.7 for x1 plus 0.01 x2. So this is our x1, this is our x2, this is beta naught, beta 1, beta 2. Okay? So before we can interpret the equation, we need to look at the p-value and t-statistic for each of the independent variables. So the hypotheses are same. Null hypothesis, there is no linear regression, linear relationship between wire length and pole strength, right? Alternative hypothesis, there is a linear relationship between wire length and pole strength. You can do two hypotheses lah. You need to do two hypotheses. First for wire length, another one is for die height, right? So same as previous, our p-value alpha equal to 0.05, p-value equal to how much? This is p-value for wire length is less than 0.001, right? Which is very small, right? So this one less than 0.0001, and our decision null hypothesis is rejected because the p-value less than 0.05. Conclusion, there is a significant relationship between wire length and pole strength. So you replicate this step for die height. Okay. Not okay? Okay. Now, for coefficient table, we're going to look at the p-value, right? So in this one for p-value lah. If in exam they ask you to use t statistic, then you need to use t statistic. But in faster way to identify whether there is a significant relationship, look at p-value. So now we are doing for wire length, relationship wire length and pole strength. So the null hypothesis, there is no significant linear relationship between wire length and pole strength. Alternative hypothesis, there is a significant linear relationship between wire length and pole strength. Our alpha 0.05, our test statistic, make sure you put like this, test statistic, p-value, decision rule, decision and conclusion. This one I shortcut. Okay. Our p-value less than 0.001. Why? Because it's very small, right? Look at this one. We have 18 0 in front of 3, right? So means that kalau it's very small, we just put like this, less than 0.001. I don't need to put 0.000 kira sampai 18, no need, right? And the p-value less than 0.05. Decision rule, if the p-value less than 0.05, null hypothesis is rejected, then since the p-value less than 0.5, kita reject. We reject null hypothesis. Conclusion based on alternative hypothesis. So the conclusion will be there is a significant linear relationship between wire length and pole strength. Okay, so you replicate this step for die height. For the next variable, we have two variable, right? First, currently we are doing for wire length, and you replicate the same step for die height. Okay, so to confirm this value is significant, we look at the confidence interval. So based on the confidence interval, zero value is not within the range, within the interval, so the p-value should be less than 0.05. Same goes to die height. Okay, so this is a repeated value lah, right? Okay, now since both independent variables are significant, Now we going to interpret the equation. So equation y equal to 2.26 plus 2.74 x1 plus 0.01 x2. Right. So for beta 1, which is x1, right, wire length, right, beta 1 equal to 2.74. It means that for one wire length, this one maybe I just made up 1 centimeter increase in wire length, the pull strength will also increase by how much? 2.74, provided die height hold constant. So when die height is not is hold as a constant, for every 1 unit increase in wire length, the pull strength will also increase by 2.74. Right? If this one, because we have a positive beta 1. If beta 1 is negative 2.74, for 1 unit increase in wire length, the pull strength will decrease by 2.74, provided die height hold as a constant. So for die height, beta 2 equal to 0.01. So for 1 centimeter increase in die height, pull strength will increase by 0.01, provided wire length is whole as constant. Right. So it's the same interpretation, right, as in a simple linear regression. Right. In this case, we have more than 2 independent variables. So for beta naught equal to 2.2026. This is not make sense when wire length equal to 0, when x1 equal to 0, x2 equal to 0. Pull strength will be equal to 2.26. It depends on the context lah. When we have no wire length or no die height, which is not significant. Okay, that is how we interpret the equation. Now we move to the assumption. So we know that we have line I, assumption, linearity and normality, independence and equality of variance. And we have another one, independence of numerical variable. So let's check the first one, which is normality assumption. So we can plot, we use the plot, normality plot. If you look at this one, we can say that the data having approximate to normal distribution. Approximate, not normal distribution. But to confirm this, we can use the value here, residual value, right, to create a box plot. Maybe box plot should be more clear. We can get clear decision from there. So maybe where is a box plot? This one, right? So this is a box plot. Nampak ke? Tak kan? Right. So from the box plot, we can say that the data is approximate to normal distribution, but it's slightly skewed to the right. You know how to interpret box plot? You need to rotate the box plot at 90 degree. So it should look like this. Right. So this is a minimum value. This is a minimum value. This is maximum value. You need to rotate 90 degree. Right. So if the area on the left hand side is larger compared to the right hand side, so this is a skew to the left. If the area on the right hand side is larger compared to the left, it's a skew to the left, right distribution. If the area on the box ni equally size, then the normal distribution. Okay. This is one way to check normality assumption. Okay. So we can also use a histogram, but I think Excel shows histogram juga. Next, we need to look at the linearity and equality of variance. So XPYR, X is x-axis predicted value, y-axis residual value. So we insert the scatter diagram. So maybe I turun bawah sikit. Right. So from the scatter diagram, you can see ada sikit pattern lah kan. This is not a good data lah. Huh? So linearity assumption, maybe if you get the data equally distributed around the graph, right, around the canvas, then it will show, it will conclude the linearity assumption and equality of variance, right? Okay, this is for linearity and equality of variance. And next, we look at the individual numerical variable. So it should also show no significant pattern. Right. So this is linearity of independent variable, independent numerical variable. So maybe kita turun bawah sikit. Right. It's also show no pattern. Right. Next, we need to check for multicollinearity. So how to check for multicollinearity? We need to model the independent variable without the dependent variable. It means that we need to take out the pull strength out of the model and we model wire length and die height only, right, to get the R square. So now, maybe we go to data analysis, regression again. So now, dependent variable, I change to wire length. Independent variable, I change to only die height. Then I don't want any plot here. I don't want confidence interval. Or I need to display down here. Right. So this is the model of independent variables. Right. So we look at the R square is equal to 0. This is R square equal to 0.143196163. Okay lah. Right. So VIF should be equal to 1 divided by 1 minus R square. So it should be 1 divided by 1 minus 0.143196163. So this one should be how much? 1 divided by 1 minus 0.14316.463 should be equal to 1.1671. So this is the value of variance inflection factor. So since the variance inflection factor is less than 10, so there are no multicollinearity issue. Right. Boleh? We already explained everything here. Boleh tengok ah. This one I explain everything. Okay. You can check using Python. I think I already put it here, right? This is a full strength example. Maybe kita tengok the multi-corollary. Should be 1.167, right? Same as a value that we are calculating just now. Okay. So by using Python or R, you don't need to model another time. You don't need to model independent variable and independent variable. You just call the function to get the value of variance infection vector. Okay. So you can refer to my code, Python code here, and maybe you can try for example number 4. So I already, I think in my website I already give you example number 4, right? Data set example number 4. Okay. So now let's look at example number 3. So this is a different example. I'm not going to model it for you. I already give the result here. So we have 4 variables, right? Three independent variables: depth, gain density, porosity, and the dependent variable is RQI. We want to investigate the dependent variable between the 4 factors, right? Okay. Now, let's say we have this result. From the result, Excel result here, first we look at the R square. The R square tells us 49.13% of the total variation in RQI explained by these 4 factors, right? 4 independent variable. This is quite low because 49%, right? It's not even more than 50%, right? So if you look at the ANOVA table, this is less than 0.01, right? 68, right? So it means that the model is valid for prediction. But if you look at the standard error of estimate, 0.399. And based on the coefficient table, this variable is not significant, right? It's not real. There are no real linear relationship between gain density and RQI. Betul? Right? Okay. Betul ke? Right? So what you need to do? We need to drop that variable lah. Because the variable is not significant. We look at the p-value yang paling besar. P-value more than 0.48, 596. Variable drop. Yang besar lah. The largest p-value lah. 0.68, right? So this case, we drop on this one only one variable yang not significant, right? We drop this variable, we will get new equation, new result, right? So we have only 3 independent variables in the model. Now let's check again the R square. The R square here is 0.49, which is 49.08. Previous model, we have 49.18, which is more than the current model. So the current model is even worse compared to the previous, kan? Even though we have all the independent variables significant, right? And the standard error of estimate, right, is 3.9948. So previous one is 0.39969. Very little different, right? Previous model 3.99, current model 3.99 juga. Right, so means that something wrong with the model, with the data. So we need to check for the outliers. So check for the outliers and we remove the outlier from the data and try to model all the variables again. So when we remove outlier, we model the variable again, and we can see that the R square increased from 0.4 to 0.7. So this is good model lah. Right. And the standard error of estimate also decreased to 0.13. So before this 0.39 now becomes 0.13. And then you can conclude that this is good model compared to the previous one. Even though we have one independent variable not significant. Right? So since that is not significant, x1 is not significant, we need to drop this variable. When we drop the variable, so we will get this one. The previous model is 0.35. So this one is 0.7395. And after dropping the x1, we still get 0.7. So which is good lah, right? More than 0.5, right? And this is our final model. Okay. This is a strategy lah to model linear regression. Okay, we need to check the outliers and remodel, right? Okay. Now, linear regression, example number 4. So later on, you can try example number 4. We want to see the relationship of all independent variables towards charges of medical costs. If you notice, example 1, 2, 3, all the independent variables are numerical. In this example, we have combination of numerical and categorical. Sex means male and female. We have smoker, yes or no. Region, we have 4 regions in the data set. Right. So maybe I tunjuk sikit how to model the data. I'm using R programming. Are you familiar with R? Familiar with Python, right? Well, later on you use Python lah. I'm showing you by using R. It's the same concept lah. Example number 4. Right. So before you start with analysis, you need to check the data. You need to explore the data, understand the data. So in R, when you import the data, factor variable, it will automatically convert to character. So which is, this is not the type of data that we want. We want it to be a factor level. And children also should be numerical. So we change sex, smoker, and region to be a factor level, and this is a numeric, and check again the data. So now already check. So now let's say I model the data of multiple linear regression first time. So based on the multiple linear regression, this is a combination of categorical and numerical. Okay, it's not same as previous. So you look at the region, northwest, southwest, and so on. So let's look at the table, data 1, region. So we have 4 regions here. Right. So if you look at region, why we have only 3? But in fact, we have 4. Because we do a comparison, northwest with northeast, southeast with northeast, and so on. It's based on the northeast. So it will always compare to the first category of the data. And female, it will also compare to male. Right? Smoker, yes, will compare to smoker, no. Right? So based on the data, model, which variable is not significant? We have sex and region, right? So both are not significant. Which one is the most not significant? Just like sex, male, kan? So now we remove the gender. So when you remove the gender from the model, still it shows region is not significant, more than 0.05, northwest, right? So then what you need to do is remove region from the model. So we will get the final model here. So the R square is 0.4. This is the F value, P value for F distribution, degree of freedom, and we have the P value, T value. That's all. Right? And then you can interpret lah macam tadi, right? Okay. So you try to model this equation using Python. Right, practice now. Nanti next week you will go to lab session, right? So lab session, you will learn Python. So you familiar with Python, right? Not? Yes or no? Yes, okay lah. If you're not familiar, then don't worry. You akan belajar from the beginning. Or are you pernah dengar data camp? Tak pernah. So, all right, I have access to data camp, right? You can get full access. Kalau if you're interested to learn Python more by yourself, you can inform me. I will include you into my data camp platform. So you can learn that Python or R or any language lah at your free time. Okay. Now, so how linear and non-linear regression depend on the data? So we will discuss non-linear regression, which is logistic regression next week. Next topic will be logistic regression. So to understand logistic regression, you need to understand simple and multiple linear regression. Okay. Okay, that's all. Any questions so far? No question? Then that's all. Thank you very much. Assalamualaikum. All right.